Typically makeup classes would be held on Friday, same class, same time. So lectures are Monday, Wednesday. Whenever we have makeup classes, I would like to have them on Friday. So the question is, and it will be recorded, so if for any reason you have a conflict on Friday, you cannot come at this time, the lecture is also available through video. If necessary, you can even have a class when I miss it and just play it back, which is really not needed, you can view it yourself. So real question is, if we have occasional makeup classes on Friday, how many of you can come? So most or fair number of you. Does anybody have any problem if they cannot come to viewing that class online for those 2 or 3 classes? Anyone have any issues with that? So between either coming to the makeup class or just viewing the class online, is it okay to schedule the class on Fridays at this time? Otherwise I have to look for some other time to have it. But it seems like that slot should be open if you are on Mondays and Wednesday as our class here. Is that fine? Okay, so the first class will be this Friday. So just to keep us moving along, because 2 weeks from now, actually not 2 weeks from now, next week, Wednesday I am not here. So next Wednesday's lecture I will just have it this Friday. Okay, I'll send out an announcement about this so you don't forget and all of that. Okay, so just keep that in mind that we will have 3 lectures this week. One of them will be a makeup lecture. Okay. Okay, so you want to start?
Get started.
So I have a few slides overflow from last class and then we'll start a new topic today. So we were talking towards the end of last class about operating systems and how they evolved. I briefly introduced uniprocessor operating systems, monolithic kernels, microkernels and so on. And we just want to use that as a background to actually discuss other kinds of operating systems that are out there. So the first one that generalizes directly from uniprocessor operating systems is multiprocessor operating systems. In fact, this is the norm today because practically most general purpose machines have multiple cores. Even phones have now multiple cores, as I mentioned, and so do laptops and so on. Okay, so multiple cores basically means that the OS that is running on those machines has to manage multiple processors. Okay, so what we were talking about from a uniprocessor world, really today the way you see how general purpose operating systems work is they're multiprocessor in nature. So the question is, how does the kernel work? So typically on a multiprocessor machine, okay, the OS is hiding the presence of multiple cores from the user. You explicitly don't need to deal with it. You just start your applications and do your work. And it's the OS's job to somehow map processes and threads to cores. Okay, you don't start an application and say run it on this core or run it on that core. The OS does that for you. So in some sense, you are getting some transparency in terms of what resources are present. Okay, so you have machine. Okay, it has, let's say, 2 cores, core 1 and core 2. The OS kernel is basically running on top and it's managing the resources. So the user is essentially sees a single unified machines and doesn't have to deal with the presence of multiple cores. And that's basically a natural way to progress from a single core uniprocessor machine to a multi-core, because nothing really has changed from a user's perspective. You just have more resources, so more applications can run in parallel and so on. Okay? So it looks like more or less the same, just that it seems like there are more resources on your machine. And this distinction is going to be important as we talk about distributed operating systems. Okay, so going from multiprocessor to distributed operating systems, now you not only have a machine which may have multiple cores, but you have multiple machines themselves. Okay, so here you have a machine with more than one processor. Now think of this as now in a distributed system, you have multiple such machines. Each may have one or more cores. So this is machine 1, this is machine 2, this is machine 3. And a distributed operating system is going to now manage this collection of machines for us. Okay? And depending on what is visible to the users and what is hidden, we'll have different flavors of distributed operating system. But broadly speaking, you want to manage resources as transparently and as seamlessly as possible now across a collection of machines. So you went from one core to multiple cores on a machine. Now you are going from one machine to multiple machines. Okay, and you want to somehow manage these resources across machines as seamlessly as possible. So the broad goal is to make it look like this collection of machines is similar to a centralized operating system. And the degree to which you actually get this abstraction will give us different flavors of distributed operating systems. So there are operating systems that will make this entire pool look like one logical machine. Just as when you had a multiprocessor or a multi-core machine, it just looked like one machine where the presence of cores was hidden from you. So there are variants that will actually hide the presence of machines and make this look like one logically unified machine. Okay, the fact that there are multiple machines is hidden from you. Other flavors will actually expose that to you. Okay, so you need to think about the transparency discussion that we have briefly had last time about location transparency, migration transparency, concurrency transparency. All of those issues will come up when you are designing this distributed operating system. Okay, and we'll just look at one aspect, namely whether the fact that there are multiple resources and multiple machines is transparent or not. But you have to deal with all of those issues in reality. Okay, so these are the three flavors that I'm going to quickly talk about. Okay, so there is this traditional distributed operating system. There is something called a network operating system, and there's a middleware operating system. So these will they do essentially the same thing. They're all trying to manage these resources on multiple machines. Okay, but they will provide different views of what the resources look like to the user. Okay. The distributed operating system is the most tightly coupled. Okay. Here basically you will have one kernel, essentially a single kernel that spans multiple machines. Just as in a multiprocessor case, one kernel span multiple cores and manage those cores for you. Take that same idea and now you can have a kernel that is actually going to go across machines. Okay. So it's one kernel, a single image that runs, and then the view that you get is a single large machine from the outside. Okay. The fact that the presence of individual machines is actually hidden from. So this is the tightest form of coupling you are going to get. Okay. So this is going to hide the presence of multiple machines and manage them as single unified machine. Okay, network operating system relaxes some of that. Okay, this is what we actually will see. You will see the presence of multiple machines. Okay, they will each have their own IP address, each have their own name, but they will have other pieces of software that will allow applications to run across multiple machines and allow them to do something useful. And what the middleware operating systems will do is take a network operating system, put a software layer on top and make it look like a distributed operating system. So the kernel itself will not give you that abstraction. The kernel will be a regular OS, but you will run a piece of software that runs on top that will try to make it look like a logical machine. And I have some pictures that will make all this clear. Okay. This is a distributed operating system. This is the picture I drew here. So you have multiple machines. Okay, they may have a kernel that is trying to manage local resources, but there is also, think of it as a next higher level kernel that spans multiple machines. So everything above this sees a single unified machine. Okay, the fact that there are multiple machines is hidden from users, applications, and so on. Okay, so you may actually have a single name for the entire machine. So you will not, for instance, log on to a specific machine in this cluster. You will have to log on to some logical name that will allow you to access this pool as if it was one unified machine, for example. Okay. So this is a distributed operating system. Applications will run on top, and OS will do whatever it needs to do in terms of managing underlying resources, allocating them to OSs and so on. Okay. And MOSIX is an example of that. Okay. It's called a single system image type of operating system. Network operating system is what we are used to. Okay. Every operating system that you find on any machine that has a network interface is essentially a network operating system. It has a local kernel and it has network services. Okay, it will have SSH, it will have TCP, IP support, all of these things that allows this machine to access other network services. Okay. So in a network operating system world, you simply have individual machines and individual kernels. Okay, and then basically the machine has support for networking support that allows it to communicate with other machines. Okay, this is essentially any machine you have today. Okay. So in this case, the presence of individual machines is visible to the users and application. You will SSH to a specific machine in this cluster. Okay. Think of the EdLab example. Right? There are multiple workstations. You will actually access a in particular one. It's not like all of them look like single unified machine from the outside. But distributed applications can still run on top because they will use the networking support for the components that run on individual machines. They use the underlying networking support to communicate. But it is not as transparent from a hardware perspective to either the application or user. You need to know component A of the application is running here and component B is running here, so you have to set up specific TCP IP connections or make RPC call to specific machines and so on. None of that is hidden from the application. Application writer, users have to deal with all of this. Okay, so is that too clear? Okay, now, so you have, so although this would be nice to have, this is a lot more complicated to make it work with. So what you have in the practice is a network operating system, which is just run Linux or Windows or Mac, and then it uses its networking support to write application. Okay. So middleware operating systems take a network operating system and try to bring back some of the nice functionality of a distributed operating system. And this is the picture here, which is you have your machine which is running a network OS, and then you write a software layer that runs on top of the OS. Okay. This is application level middleware. This is not OS support. This is application middleware. It tries to unify some of the hardware abstraction. So any application that is written using this middleware will try to see, get a view of a more unified set of resources. And you can also run standard applications that don't use the middleware. You can use your standard browsers and mail clients that will work the normal way on any network operating system. But you can then use a middleware to bring back some of the transparency aspects of a pure distributed operating system. Okay, so the middleware OS lies somewhere in between the network OS and the distributed OS in terms of how transparent the resources are, who is responsible for managing the resources. Okay, in the network OS case, the application needs to deal with what runs where and how it runs, how things are mapped to machine. In a distributed OS, the OS takes care of it. You just run an application, it figures out which machine, which course to run it on, how they all work across the cluster. Okay, and the middleware lies somewhere in between. Is that clear? So there was a picture here that I skipped, which simply shows a network OS where there are clients and servers, for instance. So you have to connect to a specific server. The fact that the server is part of your distributed system is not transparent. Okay? The clients have to specifically talk to a server and so on. Any questions on this distinction? So there's a table here which I will leave it as a homework for you to go and look at. It basically takes a distributed OS, a network OS and a middleware based OS and tries to compare it. And basically you will see that transparency decreases from a distributed OS to network OS. Middleware is somewhere in between. And complexity also decreases. And distributed OS is clearly harder to manage, provide this illusion of a single machine and so on. So, any questions on this before we switch gears? That's actually the last few slides of the previous lecture that I had skipped over. Anyone take the quiz? So you realize that we had not covered this material. The TA didn't know that. Okay, so we will switch gears and talk about architectures for distributed systems. So we actually went through chapter 1 in short order. So it's just one lecture that spans a fair bit of pages. You can go and review some of the material there. So what is important is to know what we covered here and just keep up with the class. Today we are going to talk about architectures for distributed systems. That's chapter 2. So what we will do is we'll start, this is a top-down view. Okay? Rather than looking at individual components and trying to figure out how each of those work, we'll start at the top and says how do you write distributed systems, distributed applications from an architectural standpoint. And we'll look at a slew of these architectures, maybe 4 to 6 different depending on how you group them, of different ways to write your applications. And we'll see what are the advantages, disadvantages of all of this. So we'll first start with the style of how you write your distributed system. So there are four that we'll look at here: the layered approach, the object-oriented approach, the data-centric approach, and the event-based approach. And then we'll look at another way to slice and dice the architectures for a distributed system. So let's start with the architectures. So this is a picture that shows a layered design for writing your distributed system or a distributed application. They are both the same from our perspective, an application or a system. Okay, so in this case, your application has multiple components. And components are actually layers in the overall architecture. And the way the application or the system works is each layer communicates with the layer above it and the layer below it. So you cannot have, so layer I in this pipeline can only talk to layer I plus 1 and I minus 1 in terms of how requests are actually flowing through the system. Okay? So you can't have layer I just communicate directly with some arbitrary other layer. So you are going to have this modularity and layering in terms of how the application is partitioned. Okay? So if you have taken a course on networking, you will realize that protocol stacks also behave in this fashion. Protocol stack, you have layering, and layers basically talk to the layers before or after. But the same idea applies also to how you write distributed application. Okay, this is in fact a very popular way of writing your applications, as we will see as we go along in the lecture. Lots of web applications are written in this fashion. These are all referred to as multi-tiered web application. Okay, so each layer is also referred to a tier in that case, and you will see that when you write your application, you will have tier I talking to tier I plus 1 or I minus 1, and we'll see examples of that in just a moment. But this is the layered approach at eye level. Okay? Concrete examples will come short. Object-oriented approach is a different way of writing your distributed application. We'll also see several examples as we go along in this course. So in this case, the components of your distributed applications are written as classes or objects. Okay? Objects communicate with one another by calling methods on other objects. Okay? So if you have done any object-oriented programming, Java or any of those object-oriented languages, you will realize this is the way you also write a centralized application, you have classes and objects. Okay? The only difference in the distributed world is these objects actually live on different machines. They are not part of the same process or the same machine. Okay? This object could be on one machine and that object could be on another machine and so on. And I should have mentioned that even in the previous case, these layers or tiers could be also on different machines. Okay? Because we're talking about distributed systems here. So the same is true here. So these are distributed objects. The objects could be spread across. The state of a single object could also be distributed across multiple machines. Okay? So your objects making calls on, or method calls on other objects where these objects reside on different machines. So you have to decide when you design your application how to partition it into objects and which objects or which components are essentially on which machine and what function do they provide, and then components interact with one another. Okay? A different way of writing distributed applications. We'll look at this in a fair bit of detail in about 2 classes when we talk about RPCs, RMIs, distributed objects, and so on. Third architecture to write distributed application is called event-based. Again, we'll encounter this several times over the course of the class. So here you have components of an application. So the application is distributed, you partition it into smaller pieces. They are independent components. They run on different machines. Okay? Now the way they communicate in an event-based architecture is through events. Okay? There are many different ways to write event-based application. Here is one that is shown in the picture. So there is something called an event bus, okay? And you are using what is referred to as the publish-subscribe paradigm to write your application. Okay? So what happens is components, in order to communicate, will publish events. Okay? Other components would have subscribed to events of a certain kind. So whenever a new event is created or occurs in the system, the event bus, which is sort of a middleware, is going to look at which other components have subscribed to an event of that type, and then that event is actually delivered to those components. Okay, so publish distributed application. Okay. It is somewhat loose coordination because when a component publishes an event, it doesn't specify that you have to send this event to that other component. You simply publish it, and the other component would have subscribed to a certain type of events, and depending on whether there is a match or not, you will deliver it. Okay. Slightly different way of writing an application. In other application, when you're messaging, you say here's a message, send it to this component. You explicitly address it to a particular component. In publish subscribe, you don't address messages or events to any specific component. Messages just have types, and other components are subscribed to messages of certain types, and they are just, those messages will be delivered by the event channel or the event bus. Okay, so this is referred to as an event-based or a publish-subscribe style architecture for writing distributed application. Okay. Last one is shared data spaces. Okay. This we will look at maybe in the last two lectures of the course when we talk about distributed middlewares. So this is a very loose form of coupling. It's also a form of publish-subscribe architecture, but an even looser one. Okay, so what happens in this case is components will publish events and they put it on this thing called a data space. Okay. So the best analogy I can give is a bulletin board where you go and post notices. Yeah, a physical bulletin board. Let's say you're trying to sell some old furniture. Okay. So you don't know who is going to buy it. You just put up a note saying I'm selling this furniture, and then if you're interested, you put a small phone number saying contact me. Okay. And then that you just post it, and then arbitrary people come and view the bulletin board, and if somebody has an interest, they will actually look at your message and then call you. Same is true here. Okay. So a component will basically publish either its own presence or a service that it provides onto a bulletin board. So at some later point in time, some other component may come and look for a particular service of that kind and look for a notice, and then if it finds a match, then it will go and communicate with those. Okay. This is a very loose form of coupling because messages may sit on the bulletin board undelivered for arbitrary periods of time. Okay. Once you post a notice, let's say to sell your furniture, you don't know when you are going to get a response or if you will get any response at all. Okay. Your message may not draw any interest. So you are sending messages without even knowing who it will be delivered to, whether it will be delivered to anyone, which is a very different form of communication. Typically when you send a message, you expect to know the recipient and you address it to someone. Here you are sending a message without knowing who it will go to. Yes, question.
How is this different from publish subscribe? That also publishes without any...
So question is, how is this different from publish subscribe? The main difference is in a shared bulletin board architecture, you are decoupled in what is called space and time, which means when you publish something, it will be kept for arbitrary periods of time, and then it may never get delivered or it may get delivered. In a publish subscribe or event-based architecture, when an event is published, you just look for matches, you deliver it to the matching recipients, and then you discard it. You are not going to buffer it forever. In a bulletin board, your notice may stay there for weeks or months. Okay. Here, if there are no matches, you have said, I have found out who is interested. If no one is interested, you just drop it. You don't keep it around saying, will somebody come in 10 days and look for an event that was published or something like that. The bulletin board, it stays there for a period of time. Okay. So these are also called blackboard architectures, okay, just as a bulletin board architecture. This is a very loose form of communication. I just wanted to give a quick example of where this is used. Okay. So this has become popular in scenarios where, or what are referred to as zero configuration scenarios. And the best way to think about this is, I'll give an example. Okay. Let us say, let's take the example of network printers. Okay. Now typically if you want to print from your machine, you have to configure a printer on that machine. And it could be a network printer, you have to put its IP address and whatever, and then you print to that printer and your job is sent over. Okay. Let's say you go to your friend's house or you go visit somebody at some other university, okay, and you want to print something at that location. Okay. The normal way to do it is you ask someone, is there a local printer? They'll say, yes, here is IP address, you configure it and whatever, and then you print. Okay. A better way to do it is that the printer has advertised its presence on a bulletin board. Okay. The printer says, I'm a printer. Okay, this is my IP address. If you are interested, then you basically go and send jobs to this address. Okay? And then what your machine would do is, rather than you, the user, trying to do anything, your machine will actually go and look around on the bulletin board. Is there a printer? Okay? And then when you basically try to print, a list of nearby printers will automatically show up because they have been discovered using a bulletin board. And you can just say, go print here. Okay, so there's nothing to configure because the machine went and figured out whatever is present in the environment, and you looked at and it basically presented a list of choices for you. That's all you have to do. Okay, so this is referred to as zero configuration because you don't actually have to go and every time you go somewhere you don't have to reconfigure your printers and whatnot. Okay, printer is just one example. This will apply to many other kinds of services. So services advertise themselves whenever you enter a new environment. Your machine discovers all services that are of interest, and whenever the user needs to use them, they are just presented. Here is one that may be of use to you. Okay, so that's basically, you'll see that Macs and Windows now do this. You show up in some random Wi-Fi network, it will automatically discover and show you a list of printers and so on, because there are services that are actively advertising themselves in this fashion. Okay? Any questions on this? Okay, so now we'll come back to a different way of thinking about systems, and we'll go back to client-server architectures and look at them in a little more detail. Okay, so this picture shows you a traditional interaction between a client machine and a server machine that are part of some distributed system. The client and the server are the two components of the system. So this is the y-axis here is time. Okay, so the dark line shows that the client or the server is executing. A dotted line shows that it's waiting. Okay, so the server is running, it's waiting for a request from any client. Here the client executing, it sends off a request to the server. The request traverses over a network, comes to a server. Server will receive the request, start processing it, that's why it's dark, and then it produces a response. The response goes back. The client is waiting for the response. In the meantime, as a response comes, it does whatever it needs to do. Yeah, web servers are examples of this, database servers, file servers. They all fall into this category. Okay. So that's your traditional client-server architecture. Now what we will look at is the server component in a little more detail. Because implicit here in this description I just gave you is client is one component and the server is another component. Okay? But that does not have to be the case. The server could be actually a collection of components. The server itself may be distributed in some shape or form. And we will look at that in more detail. So the typical servers will have three components. Okay? In many cases, all three components are in a single process. So the server itself is one entity. But in many cases, they will not be. And the three components are what is referred to as a user interface layer, the processing layer, and the data layer. Okay. Roughly speaking, this is the interface aspects of the server. This is the application logic of the server. This is where the actual code for the server is. And this is the data of the server. The data may typically be in a database, but it doesn't have to be. Okay. We look at how the servers will use tiering and so on to implement these three functions. Okay. Here is an example of a search engine. Okay. How you may actually write the server of a search engine using the three layers that I mentioned. So you will see that the search engine has multiple components. I'm going to explain a little bit on that. Okay, the dotted line are the boundaries between the user interface, the processing, and the data lake. Okay. Typical user interface may be very straightforward, right? The Google search engine provides you a search box. And that's all that is there for the interface. When you type some keywords and hit search, whatever keywords you type are submitted to the search engine for processing. So here is basically the so let's say a request comes into the user interface layer, just a string of words that you're searching on. Okay. So what will then happen is it will basically go to a query generator. Okay, and it will take those keywords and convert them into an actual database query. Okay. And what is assumed here is the search engine has already crawled some search web pages. And it has taken the contents of those web pages and it has put them in a database. And so that is what you are going to actually search. You are not going to go and start crawling after the query comes in. If the crawling part has been done independently, you have crawled and collected pages from the web and you have put it into a database and indexed them. So when a search query comes, what you will do is you'll take the query generator and actually generate a database query that is basically some combination of your search terms. Okay, so this is basically the processing that you're doing here. You're converting keywords into SQL queries and things like that. Okay, those are sent to the data layer. In this case, the data layer is a traditional database which stores the content for this search engine. Okay. So then out comes from the database a list of matches that may match whatever query has come in. Okay, then the query that comes out, then you have to give it to some sort of a ranking algorithm, okay, to say order them in importance based on whatever the query terms are. The ranking algorithm will basically do, depending on whatever you have written in the ranking algorithm, you figure out from all the matching results in what order to present them. You will sort them in relevance in some sense based on the keywords themselves. Okay. So that is going to then take, essentially it's reordering your search results. Okay, this from here you'll get an unordered list of all matches. Then you'll order them based on ranking and generate a ranked order. Okay. So once this is done, you have to basically hand all this data to an HTML generator. Okay, because what is actually going back to the user is an HTML page. What has come out of a database is simply some matching pages and some content from those pages. So you will take all of the ranked list of pages and you will construct an HTML page. Okay, so you are generating HTML on the fly here. This is dynamic HTML. There is no such page that was already when you typed the search query. The page was never in existence. It was generated on the fly for you. Okay, so you take this result, generate an HTML page. The HTML page then goes back to the user interface. And then that's what is sent back to the user. So this is basically how a request has come in. It's trickled through various components of the system. A response is generated and the response also trickles to various components and then it goes out. Okay. This is your request processing pipeline for a search engine. Clearly search engine is not the topic of this course. I'm just giving you an example to show you how a complex server in a client server world is not a single component. It's a collection of many components. Okay. These don't even have to run on one machine. They could all be on different machines. And logically, they are just boxes. I didn't map them onto any physical servers. Okay. So this is basically our multi-tier, the standard multi-tier architecture. There's an interface layer. Okay. That's basically typically also called the web tier, because that is doing the HTTP processing. HTTP request comes in. If this is a web application, is sending back HTTP responses, okay, using HTML. This is your application layer, also called the processing layer. This is where the application code exists. Here is the query generator, the ranking algorithm, the HTML generator. That's all application code that somebody has written, in this case for the search engine. Okay, this is your data layer or the database layer. Okay, this is where the data for this application resides. And these three layers talk to one another. As you can see, this is a layered architecture. Each layer is only talking, and there are only three, so each layer only talks to the layer above and below it. But you could have much deeper layering as well. Here there are three, which is the standard three-tier multi-tier application. Okay, any questions on this? Okay, so the client is not shown here. Okay, the client is assumed to be a browser that is outside. This is just a server. But based on this, basically what we will sort of take away from here is there is a client machine where part of the user interface resides, which may be the browser. Okay. There is the server side, which has lots of components, and part of the user interface may reside there. At least the HTTP processing part of the user interface may reside there. The application tier and the database tier is definitely on the server side. And that's a pretty standard way of implementing any web-based application, whether it's an e-commerce store, whether it's a social media application. This is very standard. Your client is a browser, okay, and there's a web-based application at the other end. Okay, and then that application will at least have three tiers in the most common case. Web app tier, web tier, database tier. Web tier may be written in any language. I didn't mention that how these things are written. You can use Java to write your application. You can use Python to write your application, PHP to write your application, Ruby on Rails. Lots of different languages that allow you to write web applications. Okay? So that's what your web the application tier is written. Database tier is your database of choice. You could store content in files. but in most cases you will store them in some database. Okay, so that is a standard way to write a tiered application, but that's not the only way. There are many different ways to slice and dice what is in the client and what's in the server. What we want is three things. Okay, the user interface, which is how the user actually interacts with the application as a whole. Okay, the application logic and the database layer or the data layer. Okay. So what I showed you is this picture, okay, where there is the dotted line is the boundary between the client and the server. Anything above the dotted line runs on the client machine. Anything below the dotted line runs on the server, one or more servers. Okay. And so what this chart is showing is there are many different ways of writing a distributed application depending on where you draw the boundary between the client and the server. Okay. This is a very standard scenario. Okay. User interface, web browser. Part of the server deals with the web browser. That's a user interface part on the server side. This may be generating JavaScript, this could be generating HTML pages, or doing HTTP processing, whatever else it does is here. Okay. The application layer and the database layer are certainly in the most common cases on the server side. But that's not the only way to write it. Okay. You can have this scenario where the user interface completely resides on the user side, and then only the application and the database layer is on the server side. Okay, so now you have taken the user interface and it's on the client. Here only these two layers are on the server. Okay. Take it to the next level. You have the application is split between the client and the server. Part of the application is on the client, part is on the server. Okay. The next progression is the user interface and the applications are on the client. Only the database is on the server. Okay. And then the very last one is part of the data is also on the client and part is on the server. Okay, so you can, depending on what you are trying to accomplish, write your application and it may map onto any of those scenarios. And here are some examples. Okay, this is what mobile apps do, as opposed to, let's say, a browser-based app. If you have a smartphone and you download a mobile app that does exactly that, let's say it's Gmail or Facebook or whatever, you have a native app on your phone or a tablet, as opposed to interacting with that same service through a browser, you will essentially get this. The user interface is certainly all on the client, on the phone. Okay. And since this is a native mobile app, part of the application is actually on the client here. Right. So it's not just the interface, but as an application. Okay. And then some part of the application is still on the server because the server is still doing some processing. Okay. Requests still go from the native app onto the server side. So the server is doing that processing, and then there's the database side also on the server. Okay, so you have now the same application has been written in a different way where more of the code resides on the client side as opposed to just having a browser. The browser doesn't actually have much. Okay, a lot of the stuff is happening on the server. So this is sort of the browser-based web application. This is mobile application. If you have a native application on your machine, you may even have this scenario where the user interface and the entire application runs here, and the application is simply connected to some remote database, and all it's doing is sending queries. All the processing is happening locally. Okay, so you can certainly have that scenario in many different cases. Okay, you can have a native, you can also think of mail as an example and look at this progression. Okay, on this side you will have web mail like Gmail. Okay, so basically the client is simply a web browser. If you have a native mail client, you're almost here. Okay, the interface and the mail client application is sitting on your client. This database is simply a mail server that has your inbox. It's sitting on the server. It's not doing anything other than your mail client is simply requesting, give me this mail record, and it's just retrieving things from the server. Okay. The mail server is clearly not just a database, but it's acting like the data layer. Okay, so you'll see that progression. In the last case, what you have is some of the data is also cached locally. This could be done for performance reasons. Okay. So rather than keeping all the data on the server and querying it every time, you could fetch mail and cache it locally. Okay. This is what happens in many mail clients, whether it's Thunderbird or whatever. You will basically see that you can actually keep some of your mail locally. If you get disconnected and you're not able to access the server or the database, you still have something locally cached. Okay. So part of the data is on the client, part of the data is on the server. Okay. So you'll have this entire spectrum. From one and depending on how you write your application, you will progress depending on which layers are there. So, just going back to that client server picture and trying to generalize it a little bit, because now we have 3 layers. This is a sort of a slightly more detailed version of what I had shown on the client server in terms of a timeline. So you have a user interface request, so it does some processing, requests come here. The app server will then do some more processing. It will make some queries to the database. The database will do some processing. Okay, so this is a request processing pipeline. It's sort of request is trickling from one layer to another. Okay, and then each layer is sending it on to the next layer. Okay, now responses are generated, so the reverse is going to happen, and that's the response processing. So database sends some query, do some processing, and run the ranking algorithm, do whatever you do there. Then you give it to the user interface layer, which may construct an HTML page or whatever, send it back. So this is the same picture, but a more detailed version of it. Okay. Now, so in some sense, even though all of these components may themselves be on the server side, if the user interface is very simple, you see that in the server side itself, there is sort of like a client-server architecture. Okay. Each tier is acting as a client of the another tier, and that tier is acting as a server for the previous tier. Okay. In some sense, that's basically how request processing is being performed. Okay. I already mentioned that the application server could be written in many different languages. Okay. J2EE, which is Java Enterprise Edition, is a popular one. Python, PHP, Ruby on Rails. All of these are popular platforms to write this application. Okay, in this case, in most cases, the user interface is actually an HTTP server, like Apache. It's simply doing HTTP processing. Okay, so you will have basically an Apache server, essentially some sort of an application server and a database server. Yeah, this could be MySQL, Postgres, Oracle, or some such database. Questions here? So this is a very common way to write a web application. So probably there will be some assignments where you may have to do something like that. Okay. So that's all I had to say about client-server style systems. So what we are going to do now is switch gears and talk about decentralized systems. These are not client-server systems. These are referred to as peer-to-peer systems. Okay, if you heard P2P, this is basically another way of writing your distributed application. Okay, so here also, the application is partitioned into components. Okay, but components are not called clients or servers. Okay, when you have something called a client and something called a server, the server is essentially providing some service that's more distinguished or more powerful than the client. Okay, that's why the client is sending requests to the server, sending work to the server. Server performs the work and sends back a reply. In the peer-to-peer world, all entities are equal. That's why they are peers. No entity is more distinguished than the other. Okay, so they can all do whatever is needed to be done by the P2P application. Okay, so that's the broad idea of what a peer-to-peer application is. Okay, so you can write many applications that form the peer-to-peer model as well. Okay, so there are lots of different applications, whether it is Skype is a good example that uses a peer-to-peer architecture. There are things like BitTorrent and others that also use the same kind of architecture. And so with that background, I'm going to talk about a little bit about how they can be written or organized. Okay, so what is shown here is a picture of a particular peer-to-peer system called CORD. Okay, it's called a structured P2P system. Okay, and the basic idea in a P2P system here, so here the entire P2P system is simply acting like a repository of content. Okay, you send in request for some content, okay, and the system has distributed this content across multiple machines, and somehow your request will be then, the system will figure out where the content resides and you will be directed to that content. So in some sense, think of this as a large distributed data repository. Okay. The way this came about, as you probably all know, is this in the early days, the music sharing was a popular but not necessarily always legal P2P application. The content were music files, and that's what you would search for and download. But in a more general case, the content could be anything. In the BitTorrent, you can actually do large downloads of software using BitTorrent, for instance. New Linux releases are distributed in this fashion, because it's a large amount of content, so it's distributed and you get it. So what you essentially need at the heart of any content-based P2P system is a way to specify some search or some query, and for the system to figure out where the query resides in all the different peers that you have in the system. Okay? And typically the way this is done is to what is referred to as a distributed hash table. Okay? So what you want the system to do is essentially maintain a table of some sort, which basically says here is the content ID and here is the machine it's stored on, some such table. Okay? So whenever you send in a query saying I want content X, you are going to do a table lookup saying which machine is content X stored on. It could be one, there could be many copies of it, but somehow you want to do this table lookup, which will then tell you this content lives on this machine. In most P2P world, there is no such centralized table. This table itself is distributed. It's referred to as a distributed hash table or a DHT. This is showing you an organization of a DHT. The way this works is we'll assume that content is numbered. You just give a number, a unique number to every piece of content, and here basically have IDs going from 0 to 15. Okay. Now what are the dark nodes? So you'll see that so this is basically the system is organized as a logical ring. Okay, that's the structure of the system. The dark nodes are actually machines or peers in your system. Okay. So what happens is, let's say you have to manage 16 pieces of content. And in a P2P system, some many cases it is dynamic, so the number of peers is not known a priori. It could change over time. So what happens is the way you do is you self-organize. If you have two machines participating in your P2P system and 16 pieces of content, each is responsible for half of the content. The third node joins and each is responsible for a third of the content and so on. Okay? So basically as nodes come and go, who takes responsibility for which pieces of content keeps changing over time. In this P2P, this is a dynamic P2P system. So what is shown here are the dark nodes are actual machines. Okay? So when a machine joins your P2P system, it picks an ID for itself and it joins a logical place in this logical ring. It can pick any unassigned ID for itself. Okay? So let's say machine comes in, it says I am going to be machine 10 in the system. Okay? If you pick machine 10, then you are responsible for all pieces of content that basically include your ID and all IDs to the next machine. Right? So if you have now become machine 10, then all queries for content IDs 10 and 11 become your responsibility. Or rather the other way around, sorry. Anything from the previous one to you, so 8, 9 and 10 will become your responsibility. Okay? 12, which was previously handling everything from 8 to 12, will now basically give some of its work to this new machine that has just joined the system. Okay, so basically 12 was basically servicing requests for all of these pieces of content. It goes from 8 to 12, which is all of these content. A new machine comes in, you'll take this space and you'll chop it up into two. And then one you will give the responsibility of everything from 8 to 10 to this node, and then you will do 11, 10, the next two, which is 11 and 12. Okay? And if some node departs, okay, for any reason whatsoever, then the next node will take all of its burden. Okay? To do that, you have to have some replication and so on, which I'm ignoring here. But this is basically how the system works. Yeah, so you have essentially a logical ring, which is called an overlay network. Whenever a machine joins, it has to pick an ID for itself, and it will take the key space. So this is also called a key value store. A distributed hash table is called a key value store, where the keys are essentially content IDs. In this case, the value is the machine that the content is stored on. Okay, so this is the key, that's the value. Okay, the value could also be the content itself, and depending on how you organize the key values. So essentially, this is a hash table that is mapping from keys to values. You're just looking for content and it's going to point you to a machine and a file name. And what is actually happening is responsibility for deciding who services what requests. Key gets dynamically assigned. No single user is saying you handle these queries and you handle that query. Okay? The nodes self-organize. Okay, and they basically, there's a structure. So you join the ring at some position and then you follow the rules. The rule says if you join at location I, all of the content ID from the previous node through I is now your responsibility. So you take over. Okay. So this is called a single dimensional key value store. This is a system called chord. Okay, so it's essentially hashing any data item with value key you are going to basically send to that node. Okay, so what happens is now if a user says, I want to search for this content, okay, so typically you will specify a file name. Okay, you may say Linux CentOS distribution 5.1 or some such thing. Okay, or you may give the name of a music file, so something like so. You'll give a string. Okay, internally the system will map it onto some ID using a hashing function. Because file names may get mapped to some particular ID. Okay. And then let's say that becomes ID I. Then you have to basically send it to the node that is responsible for keeping track of ID. So you will basically route it through the network until it reaches the right node, and then that node will do its table lookup and say this is the matching result that we have for it. Yeah, so requests are then routed to the right nodes, and those nodes will do a key value lookup from their content and send back results. Yes?
So basically as from each node, just so you're 8, you want to find out where it is.
Yeah, so your client, right? So client will send a request. Okay. You can send a request to any node in the system. Just think of them, these are essentially like server nodes. The client server node, you send a request to a specific server. Here you can think of peers are distributed. So you don't know a priori who can handle your request, you simply inject it into the system. The system will route it, saying you are looking for I, this is not my responsibility, but so I'm going to keep passing it along the ring until it reaches the right node. And then when it reaches the right node, it will do a key value lookup. Is that clear? Any questions on this? So I'm going to now show you another P2P system called CAN, or Content Addressable Network. It is analogous to chord, which is a single dimensional key value store. Here your keys have two dimensions, X and Y. Okay. So you basically, each search query has to specify not one entry but two entry, and then you are going to map and figure out where your content lives. You know, you can ask, what are these two dimensions? Why should I care? There are many. It doesn't actually matter how you organize it. You can use one or two dimensions, but here is an example. Okay, you can say, if you are searching for files, let's say, okay, you have file name. So you can say, I want to search for foo.mp3. That's a file name. Now, if you have a two-dimensional world, you can basically partition it by the file name and the file type as the two dimensions. So you can say, you can search a query, I want a file called foo, and it's MP3 file. You might also have a file called foo, which is a JPEG file, which could be completely different kind of file. So your query has now two attributes, the name of the file and the type of the file. So then you have to search on two keys, which is I want something that matches that file name and has that type. So this will give you a two-dimensional peer-to-peer network where you are now searching on two attributes. Okay, the picture here shows you these two attributes. So there is now an x-axis, so this is showing a two-dimensional space of keys. Okay, this is, think of it as every content has two attributes, x and y. So you search for both, a match for both x and y. Okay, so essentially that will be a point in this space. So think of this as all possible file names, and the y dimension is all possible file types. So depending on what file name and what file type you are looking for, you will get a coordinate in this space that represents that file name and that file type. Okay, so now what you want is basically nodes, rather than taking responsibility of keys in a certain range, they are going to take responsibility for keys in a certain space. So each node will say, I am going to basically answer queries for file names from A to D and types MP3 and JPEG, for example. So that will be this box, because this box may have two file types and maybe 3 letters of the alphabet. So each box here represents a certain space of keys that a particular node is responsible for. Okay? So you take this entire two-dimensional spaces and you partition it into rectangles and you give one rectangle to each node, saying any matching query that has this range is going to be sent to you. Is that clear? Yes, no? So basically this is one, so each of the dots here are actual nodes. Okay, so just as so when you join the system, you pick an XY coordinate for yours, that's your node ID. And so you are going to join the system in some location and then you pick a node ID, and then what happens is the nodes that was already in the system that was servicing some space will split their queries that they were handling, and you take over some and somebody else, the previous node takes over the rest. So here is an example of how this might work. So let's say there was a node here. New node joins the system and it decides to join at this location. So what happens is you take this rectangle and you chop it up into two. The old node takes over this ID. The new node takes over that ID. So the old node is now servicing all queries that have these matches. The new node takes over the rest. Okay, so let's say you are looking at all file names from A to E. Okay, you split that, saying you now do A to C, I am going to do D to E. All file names starting with that or some such thing. Okay, so you will partition it, and you can, this is just showing two dimensions, you can have arbitrary number of dimensions that do the same thing. Okay, so you could have file name, file type, file size, you can pick whatever attribute you want and then do the same thing. But two dimensions is a good way to generalize. Your question is?
Is there a one-to-one mapping between nodes and machines, or just like in the previous ring network, the machines would be mapped, could be handling multiple such partitions?
Yeah, so here in the previous case, the question is what's the mapping from nodes and machines? So nodes and machines mean the same thing. Okay. So content has ID and nodes are essentially peers that are joined the system that are handling requests for some ID. Okay, so nodes and machines are the same thing. But basically what you're doing is you have to answer, basically you have a set of content and you're partitioning who handles requests for what dynamically. The same is true here, except that you organize the content using two attributes, not one. Okay? If you had ignored the second attribute, you can take this and map it onto a single dimensional system. Like I ignore the file tab, let's just search on file names. Okay? So we search for file foo, you may get two matches in this case. You may get an MP3 file with that name and a JPEG file with that. So you then give two matches back to the user. This allows you to specify additional attributes to filter out some results that you may not be interested in. So you can always take a multi-dimensional network and collapse it into smaller dimensions. Or you can take the two attributes and merge them into one. You can say rather than searching on foo, search for foo.mp3. Okay, so both attributes are now concatenated and you create a larger key and you search for it. So you can always collapse this into smaller specifications.
One of the D dimensions be the node name on the node ID.
Okay, so one of the D dimensions, the node name. So in this case, the node names are not part of the, so you are searching for content. What comes back to you are matches, which are, here are the machines that have, here are the, first of all, the matching file names or whatever, and here are the machines that store it, and then you pick and you download from those machines. Okay? So typically you don't search for nodes when you have content-based P2P system. You may have other kinds of P2P system where you are searching for nodes or users. In that case, the value will actually be a user IP address. Okay. So Skype also is a P2P system. Okay. The way Skype works is when you have your friend list, okay, there is no central database that says who are all the users that are logged into Skype. Okay. It's not that anytime you log in, there's one big giant server that says, okay, you logged in. So when somebody else logs in, it shows you all the people that you know who are logged in. This is handled in a P2P fashion. Okay. So who is logged in and who is not logged in, essentially a table of users. You also have a separate table of all registered users in the system. Okay. All of these are content, and that is stored in a P2P fashion. So when you search, or when you log in, it will take your buddy list or your list of contacts or whatever, and it will do a search saying who all are logged in, and each of those queries will actually go to some node that is tracking whether that user is logged in or not. And it will tell you a yes, no answer, and then your client, Skype client will say these are the contacts who are currently logged in and these are the ones who are not. That's how Skype actually deals with it. And it also, whenever you log in, it also stores the IP address. Because just because you're logged in, you still have, if you want to communicate. So all of this is stored in a dynamic fashion, in a P2P fashion in Skype. That's an example of P2P application. Yes.
So is this structured as well?
This is as structured, yes. So this is structured in 2 dimensions. I'll show examples of unstructured networks in just a moment. So both CORD and CAN are structured P2P network. Structure essentially means that you know, you assign some ordering and nodes know when they join what they're responsible for and so on. When you see example of an unstructured network, it will be clear what structure means. So that's basically the next topic is unstructured P2P system. So this is also peer-to-peer system, but there is no such structure which says what nodes are responsible for and what nodes have to do. Okay, what happens in this case is peers just join this larger networks, and peers basically decide for themselves who they communicate with, okay, and what content they are going to basically answer queries for. So essentially what happens is there is an overlay network as well. So let's say there are some number of peers in your P2P system. When a peer joins, it basically decides randomly what neighbors, logical neighbors it wants. So this creates some arbitrary topology to this fashion. A new peer joins, it will pick some random number of other peers and say these are my neighbors. Okay, so you will join in this fashion. So first of all, there is no logical structure. Unlike the previous cases, you don't have a ring or a two-dimensional grid or anything like that. Okay? There could be an arbitrary network topology because peers randomly join and they randomly pick neighbors. So this gives you some arbitrary structure that is self-formed based on who has joined, when they joined, what neighbors they picked and so on. Okay. So first of all, the topology of your P2P network is arbitrary. In the previous case, it was either a ring or a grid of some sort, n-dimensional grid. Here it is some arbitrary topology. That's the first difference. Second difference is in the previous 2 cases, you based on what ID you pick for yourself, what you are responsible for is determined by the P2P system itself. Okay, so you pick IDI, all nodes, all content from the previous node to your ID is your responsibility. Here there is no such thing. You join the network and you say, I have 5 pieces of content, I am going to be responsible for answering queries for this 5 content. Okay, other things I don't care, you decide. If you other nodes want to do something, that's their job. So you can pick whatever you want to do as well. So as a result, in this case, when some user is searching for some content, you don't know who has matching results, first of all. Okay, in the previous case, depending on the ID of the content, if you sent it to the right node, you will know whether it exists or doesn't exist. Okay? In this case, you don't know whether this content exists at all. Okay? So what happens is queries propagate in this network by a technique called flooding. Okay? You say, I want to search for food or in P3. You don't know, is this file present in my system? Who has it? Okay? Because there's no structure. You just have to search. So this is flooding is equivalent of doing brute force search. Query has to go to almost every node that is reachable, and you get all the responses back. Okay, so this node will basically search its local table saying, do I have it? Okay, yes or no. And then it will basically send it to all its neighbors. Okay, so it has picked 3 neighbors, so it will send it to those 3 neighbors. So each of those neighbors will do a search themselves, and they will send it on all other links that they have found to their neighbors. Okay, so each neighbor will keep, so you are essentially flooding the network. So the query will basically go to flood the network and responses will come back, and you keep aggregating the responses. You will take all the responses that came from you, you will take your own result, you will concatenate them and send it back to whoever sent you the questions. Okay, so it will come back and then eventually you will get all the responses. Okay, so there is no structure, so you have to search everywhere and you have to do it by flooding. So the question is this a complete graph? So question is there connected? Right? So typically the graph will be connected, okay, but flooding is not a very efficient way to do anything, the equivalent of doing brute force search. Right? So, and you may have, if you have a very large network, you may have millions of nodes and millions of users. So you don't want every time a user search for something, a lot of query coming to you when you have like 5 files you're sharing, you're answering tens of thousands of queries every time your answer is no, and you're simply sending it. So that doesn't sound very efficient. So typically when a query goes in, what you do is you do flood, but you flood with some limits. Okay, so you say, I'm going to look for all nodes that are within a distance k from this node. Okay, so you attach a hop count to the query. Okay. So whenever a query comes to you, you decrement the hop count and you send it to your team. When the hop count goes to 0, you stop flooding. Okay, so depending on the hop count, how large or how small you pick it, you will either flood the entire network or you will only flood a part of the network. If you have a hop count of 2, you are searching for all neighbors of distance 2 from this node. At that point, the query will stop propagating to that. You pick a hop count of 100, pretty much there's a good chance you'll flood the entire network, depending on the diameter of the network. Yes.
So, is there some condition enforced based on the depth of the tree?
Is there a condition enforced based on the depth of the tree? First of all, these are unstructured, so they are all organizing themselves. So in many cases, you may not know the diameter, and the diameter will keep changing because nodes in a P2P system are not necessarily assumed to be stable. They come and go. Okay, so you don't know. So this is typically a client configured parameter. When you have a P2P client, in many cases you can actually set that in your preferences. How deeply do you want to serve? There will be a default given to you, but you can change it. And whoever designed the application decides whatever that should be.
Is anything cached?
Is anything cached? So that's a good point. So you could cache some of the results that came back to you. Okay, and then when requests come in, you can use those cached results. It's a design decision. The early versions did not use that. They simply went and started flooding. So random nodes who just joined the network would start seeing surge of requests. Okay, and so there are other ways to handle this flooding problem, and I'll show an example. Caching is not typically used, but there are other ways to organize it to reduce the traffic burden. And I'll talk about that in the next slide. Yes.
So if there's like cycles in the topology, like if you're doing multiple hops,
Yeah.
does that become a problem?
Yes, that's a good observation. So when you have flooding, clearly the same query is going to propagate back to you in most cases. Like you send it here, this sends it there, and then this may go back this way. And then the node that started it got the query again. So what you have to do when you flood is you have to keep track of all the queries that you have propagated in the recent past. Okay? And if through some cycle that query comes back to you, you drop it. So I've already seen it. I'm not going to re-forward it and then keep on. Then you will never end. You just keep cycling. Right? So you have to do things like that. So you don't, if it comes back to you, you drop. So then at least, although there is a cycle, you don't have go into infinite loop at least. Right? Yes.
So when there's a hop count, there is a chance the content is actually present in the network but not found. So is that a design decision of?
Yes. So clearly, when you are going to do a brute force search, but you don't search everything, you will miss things. Okay, it could have been the content may be present at distance 8. You pick the hop count of 6, so your query never got that far. Okay, that's a chance you take, right? So you don't say, oh, I didn't find it, let me increase the hop count. You just assume that it's not there for the moment or something. So that's the way it goes. Right? So you are not going to get perfect matches all the time.
Yes. One question is that is it a decision that you take, like if the graph is big enough, then you can have such kind of systems, whereas when it's too small, then it doesn't make sense to have an unstructured P2P system. So does the evolution of graph play a
Yeah, so there is a lot of work that has been done. So you're asking about how graphs evolve and should you change it from structured to unstructured. So clearly there is I won't go into this, but there is a slide I was going to show here, and there is a description in the book which says any unstructured system which has arbitrary topology, do some simple changes in who talks to who, which I delete that edge, I add this new edge, can be reconverted to a structured system. to a sort of a known algorithm. I won't go into that here. I just wanted to kind of give that. So here is an unstructured system which seems like some arbitrary node edges, and then through some simple changes, it has changed itself into a torus, which seems like a structured organization. Right? So that protocol is in the book. I'm going to ignore that here. But that said, that's not used in practice. It's not like this. This seems like a nice algorithmic cool thing, but it's not that you write a code saying that the graph has become large. Let's reorganize ourselves and become structured. You either pick a structured system or you pick an unstructured system. That's the way it goes in most cases. But you can, if you want to do this graph reorganization, network reorganization. Okay? But coming back to the question of caching, so although after a while when your network becomes large and the number of users grows, you will start seeing lots of queries. Okay? So you want to somehow reduce the traffic that each user sees. Okay? And there are two ways to do this. One was what was mentioned, which is you cache results from prior queries. So if a new query for the same content comes, then you don't send it, you know what the result is. But if the content itself is changing over time, then cached queries may have outdated results. Okay? So a new way to organize it, or not new, rather a different way to organize it is you take your P2P network and you cluster them into smaller groups, and each group elects a leader, okay, called a super peer. And then what other peers in their group do is, rather than them having their tables of content, they just deliver their content and their IDs to the super peer. So the super peer has all the entries for everything that is in its group. Okay. So now what happens is queries only propagate to the super peer, and the super peer is answering queries on behalf of other peers in their group. Okay. So whenever a new peer joins, if there is a super peer, it will actually say, here is what I have, you answer queries on mine. Okay. So if you run this leader election well, which means you pick either more powerful nodes or nodes that are well connected over a network, okay, rather than a home cable modem, I'm on a gigabit LAN. Okay. So you pick that node, so it will basically, even though it may see a lot of traffic, it will be a small fraction of its network usage or its resource usage. Okay, so you can handle that traffic. So Skype actually does this. I said Skype is a P2P network. It's not like every Skype client is not answering hundreds and hundreds of queries. But you will see occasionally if you plug in your machine to a good network, you may start seeing a little more Skype traffic because some Skype machines have elected you as the leader. So there are super peers. So if you become super peer, then you will start seeing more traffic. So over long periods of time, since it's a free application, you have to contribute back to the network. And this is how you contribute back. You become a super peer for some group of Skype nodes. Okay? So that's the way to reorganize, which is add hierarchy. Okay? So you will basically have the same dynamics, but then you take a collection of peers and you elect a leader, and that leader will sort of do whatever it does. So now everything that was happening between peers is only happening between super peers as far as answering queries is concerned. Questions here? So there are two more architectures and maybe only 5 minutes. I'll go through this quickly. So we'll come back to this. So another architecture is, rather than just looking at what is referred to as a client-server architecture, you can have what is called a client proxy server architecture. Yes, we have. So there are 3 components, not just a client and a server. There's a proxy. Okay, proxy is essentially like a server, but it's an intermediary between the real server and the real client. Okay. So request, what happens is, rather than the client sending a request directly to the original server, it will send it to the proxy server. Okay. So the proxy server may typically have a cache. This is a popular way of building your application. The proxy server has a cache. It is caching content from the original server. If you have a match, then you send back the response immediately. You don't have to send the request all the way to the original client. Okay? So proxies are typically caches, or they could actually be providing the service itself, but think of them as caches that reduce the burden on the server. Also, proxies can be deployed closer to the clients. Okay? The remote server is wherever it is, maybe far off from the client, but you can deploy a proxy on the same LAN or somewhere close to the client. So rather than going to the far off server, if you have a copy of whatever you're looking at locally, you'll get a response faster. The server load is reduced. Okay, so these type of systems are referred to as edge server system, also called content distribution systems or caching systems. Okay, so what is shown here is there are edge servers that are placed close to clients. So here is your original server. So the client is actually first going to look at the cache before, and only if it's a cache miss will that go to the original server. Okay, so when we talk about web caching and content distribution, we will look at edge servers again. But the thing to keep in mind is, rather than a client server, you can have a client proxy server architecture. And the proxy is like a server acting like on behalf of the server. So in the context of both caching and P2P system, there is also this entire class of systems called collaborative distributed systems. Okay, they are both P2P systems, but they provide incentives for collaboration. BitTorrent is the simplest example of this system. Okay, BitTorrent is a P2P system. Okay, and the way it works is actually shown in the picture. There is a BitTorrent web page. There is something called a torrent file, which is essentially the index that says who has the file. There's something called a tracker that stores the torrent files and tracks which are the peers that have the client, the content itself. The content is chunked and distributed across multiple nodes. So what BitTorrent does is first it looks at the torrent file. From the torrent file it finds a tracker and says who has this content. The tracker will say these are the machines. And then you connect those to those machines and download content in parallel. So that's how the P2P system is. But what is interesting here is not how the P2P system itself works, but how it enforces some notion of altruism and collaboration. Okay, so P2P system, the big problem was you download from other peers, but you don't give back to the system. Okay? What BitTorrent does is it basically sees how good a client you are. If you downloaded more than you uploaded, then it will reduce your download speed. So you start seeing worse speeds for download. If you start contributing back to the system, it will increase your download speed. So now you have an incentive to say, I'm not just going to get something and then just shut the client down and never give back to the system. So next time I try to do this, it will have tracked that you haven't contributed anything back. So it will reduce your incentive. Yeah, so this is basically a way to provide incentives to users. Yeah, so basically, if P sees Q downloads more than upload, then you reduce the sending rate. So you are tracking what each peer has done, how much they have contributed, how much they have taken from the system. So if you consume more resources than you donate, then you start seeing worse performance because that's how the system is designed. So it incentivizes everyone to participate and reduces this notion of what's called freeloaders. Yeah, freeloaders just take, never give. Yeah, so that's basically another way to build distributed application using volunteer resources. Yeah, so I am going to actually stop here. There's only one slide remaining. But I did want to introduce Tian, who is our TA. She's actually sitting in the back there. I did mention that you would ask her to come and say hi to you. So just wanted to introduce who she is. You'll probably see her often in the course, in the context of the lab assignment and so on. Okay. So we'll stop here for today. Continue on Wednesday.